is Logan McGuire, and today I'm discussing the effects of artificial intelligent agents on linguistic diversity of model processing. A few details about me is that I currently attend Tunstall High School in hopes of majoring in computer science at George Mason University. A few reasons why I see this topic as important is because AI is growing at a rapid rate, leading to an exponential growth of advanced technology faster than expected. AI can also be generation tools to analyze large amounts of data within healthcare, business, education, and even translation in order to provide necessary insight on a very complex level that humans are typically incapable of. With our society being at the age of technology, AI is playing a crucial role in the success of competitors who decide to implement their models into companies' advertisement, product design, and marketing. Such booming growth in AI popularity, seemingly thought of as impossible just a few years prior, is vast enough to be considered a revolutionary change to our current age of technology. The potential of AI is rarely considered, even with its ubiquitous presence in our everyday lives. Over the past year, we have witnessed a significant increase in the adoption of AI across various sectors, underscoring its ability to apply to a wide range of needs with precision and relevance. AI consists of various models, each with unique processing features that apply to an ample array of outputs. The core intention behind these models is to deliver responses that are not only precise, but also relevant, accurate, and original, matching the diverse requests of users. My focus has leaned towards understanding AI's linguistic capabilities. Take, for instance, large language models like ChatGPT. These models based on probabilistic algorithms of words on a large scale are rapidly evolving. This brings us to the intriguing aspect of AI and its diversity in response generation. This research has delved deeply into how AI evaluates and presents diverse scripting cues, pointing to a model's advanced understanding and adaptability. Intelligent systems are summarized under a broad basis of artificial intelligence computer systems, typically to perform complex tasks that require large sets of data. All models follow practical attempts to identify and distinguish variables in order to carry out a specific task. The design of intelligent systems is mathematically coded to process information on par with a human's high cognitive function. Such factors require different outputs depending on the circumstances of implementation, thus dividing identification of algorithms to fit into a more precise and specialized framework. This division allows AI systems to adapt to a diverse range of applications, from simple decision-making processes to solving intricate problems that traditionally require human intelligence and expertise. The divisions of AI are often broken down into layers of machine learning, deep learning, and artificial neural networks, all of which are interconnected yet distinct in their functionalities and applications. Each layer represents a step forward in the complexity and capability of an intelligent system. At the base is machine learning, which focuses on enabling machines to identify patterns, make decisions with minimal human intervention. This layer involves algorithms that can process and analyze large data sets, learning to perform tasks by generalizing from examples. Building upon machine learning is deep learning. This subset involves a layer of neural networks that mimic the human brain's structure and function. Deep learning allows machines to process and analyze a level and depth of complexity not achievable with traditional machine learning algorithms. At the most advanced layer are artificial neural networks. These are key components of deep learning, consisting of interconnected nodes, or neurons, that simulate the way the human brain operates. AI models derive their ideas and compositions from human-generated data and rely on human-influenced sources for processing and analysis. These models can formulate new ideas, but cannot create them independently without a reference source. The capability of an algorithm, set by its parameters and training, largely defines the uniqueness of each output produced by different AI models. This suggests that while model upgrades may reduce repetitiveness, they don't necessarily improve the decision-making quality or creativity. ChatGPT-4, as of latest and most advanced publicly accessible large language model, demonstrates a wide range of interpretive responses, showcasing its versatility and depth in understanding diverse topics. AI outputs mimicking human-like creativity are based on data patterns rather than actual inspiration or consciousness. This suggests that while AI relies on pattern recognition, its language processing can be indistinguishable from human diversity, reinforcing its attempt at uniqueness. The integration of AI agents in linguistic applications is crucial to dissect the role of AI's evaluation and presentation in diverse and unique scripting cues. ChatGPT-4 consistently implies this when providing outputs to users, as there is no specific pattern that has been analyzed relating to a finite pattern of word differentiation. The question that my study addresses is what are the effects of utilizing an intelligent virtual agent to generate creative scripting cues on linguistic diversity compared to employing predefined scripting cues. This can be represented formally through the null hypothesis. If the intelligent virtual agent produces any artificially generated prompts, then there will be no difference in the linguistic diversity of scripts. And the alternative hypothesis states that if the intelligent virtual agent is used for producing any artificially generated prompts, then there will be no difference there will be a difference in the linguistic diversity of unique content compared to employing predefined generated scripts. Foundationally, the gap in analyzing these formats that only seem to entail anthropomorphic interpretation for participants of the model's output led me to craft my research hypothesis about prompt formatting and diversification. The materials that my study were based around were the previously mentioned latest model of ChatGPT-4. The custom-built personal computer that is used consists of an NVIDIA 1060 GTX graphics card, 32 gigabytes of Corsair RAM, an AMD Ryzen 5 3600 6-core processor, an SK Hynix SSD, and a non-disclosed power unit on a 64-bit operating system. All of these combined components were visually and mechanically inputted with a monitor and keyboard and must function on an online server with a stable Wi-Fi connection from a modem. I began my procedure by powering up my computer and loading my subjective browser of choice. From there, I was able to access the model page for ChatGPT-4 on OpenAI's official website. Instead of opening 40 tabs for the sample size, the model allowed for the creation of 40 separate instances. Following this was to apply predetermined prompts to the models, which stated directly the following: generate only a sentence, and for the next 20, generate only a unique sentence to act as the independent variable. Finally, the model's output of each sentence was measured between types and tokens and compiled in Data Classroom. A ranking was used to establish different words types and a frequency to establish the amount of recurring words. This graph represents the group of generated script samples. The values gradually range from 0.77 to 1 and only have repeating values to compare themselves 3 different times. Therefore, 14 out of the 20 ratio values support a lower confidence interval. A unique scripting cues closely range from 0.88 to 1. A major aspect of the unique variables are the repetition at a very high ratio, 6 of which are repeated at a value of 1. This gives us a 10 to 10 repetitiveness scale for a confidence interval that accounts for higher than the generated group. Comparing both of these samples' total means together gives us a simpler visualization in the difference of values. The primary relevance that summarizes my data between both groups of means portray each variable's overall ratio of ratios for the produced sentences types and tokens. These ratios being 0.8958 for the generated group and 0.9562 for the unique group prompt that they portray closely similar resulting implications. Each of these values contribute to forming a grand mean of 0.926 for all samples, which lead us to find the normal distribution of isolated values and combined values. These provide each group's means with a standard deviation, the generated groups being 0.0932 and the uniques being 0.0539. Since my raw data was collected and falls under a ratio that measures the differences when comparing groups of means, my test falls under a one-way ANOVA. At the 0.05 level of significance, my null hypothesis was rejected, meaning that there is sufficient evidence to conclude that the complexity contributed to a prompt directly influences the variability of the produced linguistics of an intelligent system. This provides contextual emphasis that the accessibility to data size is congruent to reducing the repetitiveness of produced sentences and sentence format. Based on the difference of generative and unique script format, there is a positive correlation between the complexity of the request and the diversity of the model's response. This finding can be supported by previous research conducted by Young and Shishido, where the difference between influence was how the model processed feedback. Since the language models utilize partial reinforcement learning based on what the user has provided, in addition to archived data, my study's findings reflect that the script is then considered to be a form of data availability and must direct the model's output in one way or another. However, the difference from which Young and Shishido measured upon was the application of quality. This can be represented by deductive interpretation of speed of processing, biased interpretation of overall model performance, or the comparison of one model type to another. In contrast, my basis of divergence closer relates to a study undertaken by Jane, which evaluates the creativity based on AI creation. This depends on the attitude where the descriptive tone directs the model's intelligent system's rationale. Perhani et al. Argues that AI can behave intellectually, while Gretsch et al. Denies creativity as a form of aspect for AI output. Although representing similarities to my results, these previous literatures rely on an opinionated interpretation of a qualitative analysis, which is void for my quantitative identification of the functionalities of a model's product. All of these ideas coincide to support that there is a diverse learning aspect in automated code, which enables AI to exhibit behavior akin to intellectual motif, but also processes that contain the ability to adapt to responses and reply with a unique answer. Limitations can range from biases present in training data and the time gap in which a model cannot incorporate fixed and updated knowledge. This cutoff is one of the examples that using a model that is dependent on the private ownership and maintenance of the company OpenAI. Consideration of employing a different model or developing a custom-made model tailored to the specific needs of a curated data set that is thoroughly vetted to minimize biases is the major aspect of finding the limitations of the study. By understanding the strengths and limitations of artificial intelligence systems, researchers can work towards applying artificial intelligence agents to be more reliable for real-world application. Critically, the complex systems of hospitals, government facilities, and financial institutions and compute clusters that compile extremely large sets of data could ultimately benefit from a systemic interpretation of a main-centered learning algorithm. The key takeaway that this research has come to is how beneficial research is to understanding new concepts and ideas that seem to appear in our society. Are there any questions? Yes, Mr. Tellerico.
So just curious, I guess, because AI relies on knowledge it gathers from the environment, do you expect this test to be repeatable as AI develops and gathers more information?
Yes. So what Mr. Tellerico asked was if the future research could continue even though it is only based on previous data that has been collected. I think that the previous research only means to improve it because the size of the model is very relevant to the parameter size. So ChatGPT-4 has a 200 trillion parameter size in training that the data has, and previous models of ChatGPT-4 were at only 175 billion parameters. So this major increase has shown a difference in how the models act and how they output to users' input.
Thank you.
Ms. Collins.
Good job. Have you compared which one did you use?
ChatGPT-4.
Have you compared it to any others to see which one you like better?
So Ms. Collins asked if I've compared ChatGPT-4 to any other models. No, I have not. It would be a very good consideration for future research to apply different models to each other. The reason I chose ChatGPT-4 was because it was the largest model at the time that was open source for people to use. And Mr. Taylor.
Yeah, so I was looking back at your procedure where you went into the prompt to say produce only a unique sentence. And I was just curious how you go from, and maybe there's no other way to do this in ChatGPT, but you went from produce a unique sentence, but your measure, your TTR, was individual words, so like unique words compared to overall number of words?
Yes. So those words of what the type token ratio are repeating words that occur inside of the sentence. So words like and the that may be repeated in the words are not unique words, since they will be repeated in the sentence, and that's how it's measured. And then that is given a ratio of how many words are actually in the sentence.
Yeah, so I guess my question comes back to maybe the prompt in ChatGPT where you have produced a unique sentence.
Mm-hmm.
So I guess when I hear unique sentence, I think a sentence that doesn't exist except the way that it's written. So like that exact sequence of those exact words, that's what I picture when I think of unique sentence.
So when I added a unique to my prompts control, that only accounted for adding more words to my input, which I then thought would narrow the amount of words that would occur in the next sentence. So I would assume that the next sentence wouldn't have many words repeating themselves, and it would go into something completely different from what the other independent variable measured. Yes, Ms. McGuire.
Do you believe your results would be reproducible for a larger sample size?
Ms. McGraw asked if my results would be better for a larger sample size or could be repeatable. I do think that a larger sample size for the models, and as well as the amount of words that is requested and given to the model, would vastly change the outcome.